In this lesson, we're going to be talking about related rates. In some real-world scenarios, there are rates of change that are related to one another. For example, as water is poured into a pool at a certain velocity, the volume of the pool is increasing. When we solve related rates questions, we're going to follow these guidelines. We're going to write an equation using any key formulas. Then we'll use the chain rule to differentiate implicitly with respect to time. And we'll substitute any known values to solve for the desired value. For each of these questions today, unless stated otherwise, we're just going to leave our answer in an exact form, not rounding. Number 1, air is being pumped into a spherical balloon at a rate of 500 cubic centimeters per minute. I want to point out as I'm reading this, when I see that cubic centimeter, I know that we're talking about volume here. When the radius of the balloon is 20 centimeters, how fast is the radius of the balloon changing? So, since we're talking about volume and we're talking about a sphere, we have to recall from geometry the volume of a sphere formula, which is V equals 4/3 pi r cubed. Now, there are two variables in this equation. We have V and we have R, and they're both changing. As the radius is changing, the volume is changing, and that's what we call related rates. Two rates that are related to one another, and they're both being altered here. So we're going to take the derivative of this entire equation. When I take the derivative on the left, we're going to write this as dv dt. That's the derivative of volume with respect to time. On the right, I'm going to use the power rule, bring the 3 down, and then I'm going to have 4 pi r squared. But using implicit differentiation, we know the radius is changing too, so we have to put dr dt at the end. Once we have our equation and we've taken the derivative like we've had here, we're going to go back to the problem and substitute in any values that we know. So I know the rate of change of the volume is 500. I know that the radius is 20. And I do not know what dr dt is, so I'm just going to leave that there. Okay, and I'll zoom back in. All right, if we take a look at this, we have 500 equals, let's simplify or clean this up a little bit. So we have 4 times 20 squared. Well, 20 squared is 400, times 4 is 1600, and then we'll put pi in, dr dt. And when we solve for dr dt, we're going to have 500 over 1600 pi is equal to dr dt. So that is the rate at which the radius is changing of this spherical balloon with respect to time. All right, let's look at another. As it's raining, a circular puddle is expanding at a rate of 5 millimeters squared per second. The squared in there is telling me that I'm talking about area. How fast is the radius of the puddle expanding when the radius is 98 millimeters? So let's start this off by writing area equals pi r squared because that's our area formula for a circle. So you have to pull from the problem a few key pieces that we can use to put together an equation. So we know it's circular, we know we're talking about area, and that's why I chose area of a circle formula. Now let's differentiate. So this is going to be dA dt. Use the power rule over on the right, so that's 2 pi r dr dt. Okay, remember, anytime we are taking the derivative of a variable in these problems, we're going to basically tack on an implicit notation here of dr dt, or in the previous problem we had dr dt as well, dA dt, whatever it happens to be. Any variable, we're going to tack on the implicit differentiation showing that. All right, now that we have our formula set up, we have our derivative taken, we're going to plug in everything that we know. So we know the radius is 98. We're looking for the rate of change of the radius, so we're looking for dr dt, and we know that the rate of change for the area of the circular puddle is 5. All right, so we can clean this up a little bit just like we did on the previous problem here. So this is 5 is equal to 196 pi dr dt. And when we solve for dr dt, we get 5 over 196 pi. Okay, and and that would be our answer for number 2. Number 3, all edges of a cube are expanding at a rate of 2.5 centimeters per second. How fast is the volume of the cube changing when each edge is 12 centimeters? So we can see here clearly we're talking about volume. We see the word actually given to us rather than the unit. And the volume of a cube formula is V equals A cubed. I would not use the letter E to represent the length of the edge. I would not use E for edge because we have seen E in a different problem and we're talking about logs and exponentials, and that represents different derivative rules. So I would just use the A here. So when I take the derivative, I'm going to get dv dt equals 3a squared dA dt. We are looking for a dv dt here, so I'm going to leave that. The length of the edge is 12. The rate of change is 2.5. And when I plug that in or simplify it, I'm getting dv dt is 1080. So those first 3 questions are all relatively similar to one another. You're going to see in number 4 and also in number 5, we have a little bit of a different scenario going on. Number 4, the top of a 17-foot ladder is sliding down a vertical wall at a constant rate of 2 feet per minute. When the top of the ladder is 8 feet from the ground, what is the rate of change of the distance between the bottom of the ladder and the wall? So the first thing I'm going to do for this problem is I'm going to draw a right triangle because we know that the ladder is leaning against the wall. And it also tells us that the ladder is 17 feet. So I'm just going to label that. Then we know that the top of the ladder is 8 feet from the ground. So this is 8 over here. And it doesn't tell us how far the distance the base of the ladder is from the wall. However, using Pythagorean theorem, or if you know Pythagorean triples, that tells us that this is going to be 15 feet. If you were not sure of that and you did not know the Pythagorean triple, you can use Pythagorean theorem, a squared plus b squared equals c squared, to solve for that missing leg. Now let's talk about the rates. And I'm going to put these in a different color here so you can see. We know that the top of the ladder is sliding down the wall at a rate of 2 feet per minute. And since it's sliding down, the height is basically decreasing. So I'm going to label this as -2 feet per minute. That's basically showing the top of the ladder sliding down the wall. That is the rate of change of the height compared to time. As the height decreases, almost picture the ladder. The distance of the base of the ladder from the wall is going to be increasing. So that's a new rate, and that's basically what we're being asked for. It says, what's the rate of change of the distance between the bottom of the ladder and the wall? We don't know what that is, so we're trying to find that. Now let's talk about the ladder itself. The ladder is 17 feet. We are not increasing the length of the ladder. We are not decreasing the length of the ladder. It is just 17 feet. So we're going to say the rate of change of the ladder is going to be 0. Now that we have this set up, we are going to use Pythagorean theorem as our equation in this problem. When I take the derivative, I'm going to get 2a dA dt plus 2b dB dt equals 2c dc dt. And now let's start plugging everything in. If you remember from Pythagorean theorem, it does not matter which leg is A and which one is B. So I'm just going to call this one A over here, this B, and this C. All right, so let's plug in variables now. So that's 2 times 8 times -2. Okay, so I'm plugging in for each of these variables. B, 2 times 15. I do not know what dB dt is. That's what we're trying to solve. 2, 17, and 0. And we can see that that's all going to equal 0 in the end. All right, let's clean this up a little bit. So we have -32 plus 30 dB dt is equal to 0. Let's try and get dB dt by itself. So I have 30 dB dt equals 32. And when I divide here, I'm going to get dB dt equals 32 over 30. If you wanted to reduce that, you could definitely do it to get 16 over 15 by dividing both pieces by 2. Notice that we got a positive value. That means that the distance between the base of the ladder and the wall is increasing, just like I showed in the picture before. All right, our last one is going to be the most difficult one. So it says we have an inverted cone and it's leaking water through a hole at a rate of 0.8 cubic centimeters per minute. So what that basically means is the cone is upside down. We can picture a hole in the bottom and the water is basically leaking out. The cone has a height of 10 centimeters, so I'm going to draw that in here. And a radius of 2. We can put centimeters as well. Now it says find the rate at which the water level is dropping. The water level is basically the same thing as the height of the water. Just keep in mind what that really means when height is 3. Okay, so let's talk about this for a second here. We want to talk about when the height or the water level is 3. That might look something like this. Okay, so the radius at that point is not 2. Okay, so let's make a note that r is not equal to 2 because when you have a cone, the radius changes throughout. So we know this is going to be something less than 2. So let's find a way to try and kind of equate this. So in this problem, I basically noticed that the radius of the entire cone is 1/5 of the height because 2 is 1/5 of 10. So I know that no matter what in this problem, I can determine that the radius is 1/5 of the height because we have similar triangles here. So I can use a proportion and see that those are always going to be proportionate. Now, when I go and find the volume of the cone or use the volume of a cone formula, which is V equals 1/3 pi r squared h, I have two variables on this right-hand side being multiplied by one another, which would indicate the use of the product rule. But if I do that here, so let's pretend, those of you who are copying notes onto a worksheet, you might not want to copy it yet, but let's pretend I was doing the product rule and I was finding the derivatives. So remember we multiply our original functions in the inside. The derivative of 1/3 pi r squared would be 2/3 pi r dr dt, because it's still implicit, times dh dt. In this problem, we have a little bit of an issue because we're trying to find the rate at which the water level is dropping. That's basically the rate of change of the height. But notice how there's a rate of change of the radius. And if I take a look at this problem, I do not have any value to substitute in there. So this method is basically not going to work because I'm going to get stuck and I'm going to have too many variables. And by the way, this should be dV dt over here. So based upon that, what I'm going to do instead is I'm going to change and manipulate the original equation. And what I'm going to do is I'm going to substitute in 1/5 h for r. And then I'm going to multiply this. Just clean this up before I take the derivative. And now I'll take the derivative of it. So dV dt equals 1/25 pi h squared dh dt. And now I can actually plug in all of my values. So we know that the rate of change of the volume of the cone, it's leaking, it's decreasing. So that's negative 0.8. We're talking about when the height of the cone or the water level is 3. And dH dt is what we are looking to find. We're looking for the rate at which the water level is changing. All right, I'm just going to slightly clean this up. So I have negative 0.8 equals 9/25 pi dH dt. I don't personally love how this is a decimal and a fraction in the same problem, so I'm going to rewrite that. and I'm going to solve for dH/dt. When I do that, I'm going to first, you could do this in one step if you'd like, but I'm going to multiply both sides by 25/9. You can see we have some simplification over there, so I have negative 20/9 equals pi dH/dt. And then when I divide by pi, I get negative 20/9 pi is equal to dH/dt, and that is our answer for number 5.